Okay, let us start our second day. Our first speaker is Semeon from Bimsa. With a Blackboard talk.
Okay. Thank you very much for the invitation. It's a great honor to talk at the workshop. I'm going to talk about the subject in which the topology, algebraic geometry, and representation theory meet all together. So the subject of my talk will be the double affine Hecke algebra. Algebra. Genus 2. Genus 2. So this is based on papers with joined with Semeon and some follow-up work of my own. So the conventional double affine Hecke algebras were introduced by I.Cherednik and used in his proof of Macdonald constant term conjecture from algebraic combinatorics around 1995. So one of the key ingredients of the double affine Hecke algebra was that it is equipped with an action of SL2Z by automorphism. So double affine algebra, A.Okounkov, ground. So kind of the algebra was introduced earlier, but the main applications were in 1995. And the key feature of the double affine Hecke algebra was that it is equipped with an action of SL2Z. That's actually what kind of made the proofs possible that were inaccessible in the usual theory of orthogonal polynomials. Now I'm speaking at the workshop on integrable systems. So I have to say here a few things. That the double affine Hecke algebra is the quantum phase space of trigonometric Rügener-Schneider system.
But this is for type A.
Yes, for type A, but double affine Hecke algebras are defined for all root systems. And the double affine Hecke algebra I'm going to talk about today is not related to any root system at all.
Yes.
But of course, kind of the idea of the double affine Hecke algebras came from the quantum phase space of the trigonometric Rügener system. You look at the Hamiltonians of the trigonometric Rügener system. You look at the multiplication operators, and the spherical subalgebra, some subalgebra of this Dacha, is precisely the algebra generated by those. And that's kind of considering both the Hamiltonians and the multiplication operators on the equal footing. That's what allows for this SL2Z very rich group of symmetries SL2Z. So in particular, the matrix like this would realize the symmetry between the coordinate and momentum. So that's the duality between the coordinate and momentum, which was known on the trigonometric Rügener-Schneider system. But kind of in the Dacha, it becomes part of a much larger group of symmetries that is SL2Z. Okay, so what I'm going to talk about is the geometry, is kind of the reason why there is such a large group of automorphisms. That's of course not a coincidence at all, and it has to do with the relation between the double affine Hecke algebra and the chracter varieties. So the whole idea why there is this SL2Z action, it has a meaning. So SL2Z is the modular group of a torus. Now this is modular group of a torus. So on the torus, you can consider a group of diffeomorphisms. Quotient by the diffeomorphisms isotopic to identity. This is called the mapping class group, mod of sigma 1. So it's the orientation preserving diffeomorphisms, quotient by the diffeomorphisms, which can be continuously transformed into identity. That forms a group. And the beautiful thing is that this group is actually finitely generated for closed surfaces. And the generators for those group are the dentwists. So, sigma 1 is generated by two dentwists, dA and dB, subject to relations in SL2Z, such as the braid group relation, dB, dA equals dD, dA, dB, and then dA, dB, dA. And here I have to be careful, so I think it's fourth power actually equals to identity, right? It's the difference between SL2Z and the PSL2Z. In my case, the square would be equal to identity, but that's okay. So the reason that there is and this VAGB, you just cut your torus along one cycle, and then you essentially twist it once, say counterclockwise, and glue it back. So this is what it will do with the meridian. Let's say dA, the same with the dB. Okay, so the reason this group of automorphisms act on Daha is precisely because the spherical subalgebra of the Daha is the essentially two-parameter deformation of the coordinate ring of the genus 1 character variety. So let me say a few words about the character varieties of general surface groups. So character varieties surface groups. Okay, so we're let's say sigma G oriented it can be closed, but also there is more notion for the surface of the boundary. Oriented closed surface. Then G would be a simple affine algebraic group. Simple affine algebraic group. And with this data, you can associate a variety of representations of the fundamental group of a surface in G. Representation variety. Okay. From pi 1 of sigma to G. Well, of course, G acts on the representation variety. G acts on the representation variety by simultaneous conjugation. 1 of sigma G, right? By simultaneous conjugation. Meaning that it also acts on its coordinate ring, right? So, and inside its coordinate ring, there is an invariant subring. So there is a coordinate ring of home pi 1 sigma G. And inside this coordinate ring, there is a G invariant subring. G invariant subring. 1 sigma G. Consisting of the G invariant polynomials. This is a ring of G invariants. G invariants. Okay, so the character variety, it's not really a variety in pretty much every single example you would be interested in, is the spectrum of this ring. So meaning that we think of this as almost an algebraic variety with this coordinate ring. Well, but of course it will be highly singular, and so on, but not even reduced in general. So, but because kind of a lot of the geometric properties can be formulated purely in algebraic terms if we always work with its coordinate ring and study the properties of the coordinate ring. So character variety spectrum of O of Om by 1 sigma G. Now, the meaning of this definition is that it is really close to the space of isomorphism classes of the representations, but not really. So, inside of this character variety, there is an open dense subset, which is kind of which is given by good representations. So, sigma G good. And good means that they are isomorphism classes of representations of the fundamental group, which are irreducible. And also we need to require that the centralizer of their image is precisely the center of G. So anyway, so inside of that there's an open dense subset of isomorphism classes of good representations. So this is almost like the set of isomorphism. Except that it's not, but it has a nice ring. Okay. So this open dense subset of good representations is actually a smooth symplectic manifold. It is equipped with a T-abort symplectic structure, and this symplectic structure can be extended to the Poisson bracket on the entire coordinate ring of the character variety, which is now known as a T-abort Goldman Poisson structure. So chi sigma G good is smooth symplectic, and the coordinate ring of the character variety is equipped with a T-abort Goldman Poisson bracket. Poisson bracket. Oh, sorry. Okay, so let's look at an example because our starting point was the genus 1 surface, right? So let's look at the simplest non-trivial example of a character variety we can possibly imagine. Example 1. Let's take genus 1 surface and SL2C. L2C. Okay, so in this case, fundamental group is abelian, right? It is generated by two commuting generators. So by 1 of sigma is the group generated by XY, subject to the relation that their group commutator is identity, right? So this is essentially Z2. Okay, so you can study the maps from this fundamental group to SL2C, right? Those are given by two matrices. So let's say X goes to phi of X, Y goes to phi of Y, right? So in particular, the traces of phi of X and traces of phi of Y would be invariant polynomials, right? With respect to the G action, but there will be one more generator. So in this case, the coordinate ring of the character variety, is generated by three elements subject to one relation. So first element is the trace phi of X. Second element is the trace phi of Y. And the third element is the trace of phi of XY. And there will be only one relation. So there will be only one relation. So the coordinate ring, chi sigma 1 SL2C, is the quotient of the polynomial ring in three variables by a single cubic relation, which is a squared plus b squared plus c squared minus abc minus 4. Okay, so in this particular example, the Goldman bracket would look as the bracket of AB is C minus 1/2 AB. The bracket of AC is minus B plus 1/2 AC. And the bracket between B and C will be A minus 1/2 BC. Okay, so the double affine Hecke algebra, the spherical subalgebra of the DAFA would be the quantization of this algebra with respect to this bracket. So now let's look at the following. Let's look at the spherical subalgebra of the double affine Hecke algebra. So this will be the algebra with two parameters, t to the 1/4, t to the 1/4, generated by two operators. So OA, which will be the Hamiltonian of the Rugener system, and OB, which will be the multiplication operator. So OB, acting on the function in one variable, would simply multiply it by x plus x inverse. And OA, acting on the function, would be the Macdonald operator for the root system A1. So this will be x inverse minus tx divided by x inverse minus x f with a shifted argument u to the 1/2 x plus x minus tx inverse divided by x minus x inverse multiplied by f with shifted argument in the opposite direction. Okay, so the Macdonald polynomials are the eigenfunctions of the OA. In the case of higher root systems, there are more Hamiltonians. There is a common set of eigenfunctions given by Macdonald polynomials, right? So now, if you look at this OB and OA, let's connect it to the character variety. That's the main point. That's the main point with me. So let's look at their group commutator OC. Oh, sorry, their Q commutator. OA hat, OB hat, Q, right? So this is Q to the 1/4, Q to the 1/4 OA OB minus Q to the minus 1/4 OB OA divided by Q to the 1/2 minus Q to the minus 1/2. So if you introduce this operator, then you can see that there is a relation between these three operators, which will be written as the following, as the deformation of this cubic. So the deformed cubic, would go as follows. That would be q to the 1 half OA squared plus q to the minus half OB squared plus q to the 1 half OC squared, and finally minus q to the 1/4 OA OB OC, and that equals t to the 1 half plus t to the minus 1 half multiplied by q to the 1 half to the 1 half plus q to the minus 1 half t to the 1 half to 0. So when q descends to 0, so you see that at generic q, this OC is the q commutator, but as you send q to 0, OA, OB, and OC become independent generators. That's why you need 3 generators on the classical level, right? And this T is the deformation of the coordinate ring. So if it is 4 here, it's the closed surface, closed genus 1 surface. If you put here t to the 1 half plus t to the minus 1 half, this is the torus with the puncture, and that will be the monodromy of the puncture in this case. Okay, if you now, and that will be the only relation in this algebra. So if you're interested in the monomial basis of this algebra, this will consist precisely of monomials in OA, OB, and OC, such that kind of only 2 of the generators appear, and this will be literally the same monomial basis in the classical case. Basis on E. This is precisely of those monomials OA to the power m1, OB to the power m2, OC to the power m3, such that m1, m2, m3 equals to 0. Because this cubic relation allows you to resolve the product, and that will be the only relation. You can always move all generators pass through each other. So E, H, H, E is a flat 2-parameter deformation of the original coordinate ring O of form by 1 of sigma 1 to SL2C invariant subring with respect to SL2C. Okay, and this is the reason kind of now that we have the geometric origin, the mapping class group actually acts on the classical variety, and its action by automorphism raises to the quantum level as well. That's the reason for that. Okay, now what about the genus 2? So genus 2, for a 1 root system. So first we have to define what's the analog of the genus 2 Macdonald polynomials, right? So the eigen basis of this operator OA was labeled by non-negative integers, which were the irreducible representations of SL2, right? With a genus 2, with a genus 2, you would have triples of representations of SL2C, satisfying some admissibility condition, J1, J2, J3. right? So and this would be kind of these triples of integers would label the genus 2 Macdonald polynomials. So let's say that this J1, J2, J3 is admissible. J1, J2, J3, a triple of non-negative integers is admissible. Well, if J3 isn't between J1 minus J2 and J1 plus J2. J2, and also their sum is even, 2 plus J3. So this literally means that J3, kind of those label irreducible representations of SL2, that J3 belongs into the tensor product of J1, J2, and for all other pairs as well. Okay, so now you can define a genus 2 Poicare rule, which is a recursion for the genus 2 Macdonald polynomials. So, genus 2 Poicare rule. So we have a system of we have a system of equations for all admissible triples J1, J2, J3 of 2 inverse multiplied by psi J1, J2, J3 equals to the sum now of 4 terms AB J1, J2, J3 of J1, let's say plus A, J2 plus B, J3. Same with the other 3 inverse psi J1, J2, J3. And here, what will be shifted is the first and the third index, J2, J3 plus B, and J2, 3 plus X3 inverse, J1, J2, J3. Also similar sum, J3 plus B. So for certain choice of these coefficients, there is a solution to this system of recursive equations for psi, which defines a common system of eigenfunctions, defines a common eigenbasis, basis of 3 difference operators, OA1, OA2, OA3. So, and OA1, if the Macdonald operator, which I already erased, was a sum of 2 Q-shifts, here we will have a sum of 4 Q-shifts, again, A, B, and plus minus 1, some coefficients, times the delta 1, 2 to the power A, delta 1, 3 to the power B, where delta ij acting on the function x, well, where, for example, delta 1, 2 acting on this function, it shifts the first variable. First variable, that would be f q to the 1 half x12, x13, x23. Okay, so we have essentially an integrable system now with 3 Hamiltonians, right? And the phase space of this integrable system is equipped with an action of the mapping class group of genus 2 surface by automorphisms. I'll let A be an algebra with two parameters, q to the 1/4 and t to the 1/4, generated by now 6 operators. So the 3 Hamiltonians, OA1, OA2, OA3, along with the 3 multiplication operators, OB12, OB23, OB13, then the mapping class group of the genus 2 surface, sigma 2, acts on A by automorphism. Okay, so the meaning if all these operators have a meaning now. So if you draw a genus 2 surface, then multiplication by Hamiltonian corresponds to insertion of a knot along the A1 cycle by the first Hamiltonian. By the second Hamiltonian, it would correspond to insertion of a knot along the A2 cycle. Third Hamiltonian, it would correspond to insertion of a knot along the A3 cycle. And same with B. So this is B12, B23, and B13. Now the mapping class group would act by automorphisms of this algebra. I wouldn't really tell the generators and the relation of the mapping class group of the genus 2 surface, but they are well known, of course. Again, then twists and the relation between them, they will be satisfied by this action. So, but really what I wanted to talk about is this extra parameter t. So at q equals t, this algebra wouldn't be anything new. Well, I mean, we claim that we found a new presentation as well, both for the character variety and for the algebra itself. But this will be a well-known skein algebra of the genus 2 surface, which was well defined for like over 30 years at this point. But what's this parameter t? In the case of the genus 1 surface, this t was essentially the eigenvalue of the monodromy around the puncture, right? So this whole Macdonald deformation corresponded to the introduction of a puncture on a surface, and this was this extra parameter. Well, if you do it with a higher general surface, well, first of all, the mapping class group would be different of the surface with a puncture and without puncture. The character variety would be very different, and to the kind of this t cannot be achieved in this way. So, and the meaning of this t is that kind of for many years it was understood that kind of there is certainly no generalization of the Macdonald theory beyond genus 1, right? Because of that, because that t meant the eigenvalue of the monodromy, and if you try to do it for the general surface, this wouldn't work. Now, I suggest that there is another meaning of the parameter t in the genus 1 case, which also extends to one particular case here. So the character varieties can be proved with a Poisson bracket. And like I said, those are not really smooth symplectic varieties. They are kind of, but what you can prove that in the case of G equals to SLNC or GLNC and the closed group, that they are symplectic singularities. So theorem. Schedler. 2019. So, kind of, if you have a singular variety on the smooth locus of which you have a symplectic form, you can answer kind of if this was an algebraic variety, you can resolve the singularity by a sequence of the blow-up. But almost never the symplectic form from which you will start would give you the symplectic form on the full resolved smooth variety. So the case when your symplectic form would at least give you a analytic 2 form is known as symplectic singularity. But the case when this 2 form is also non-degenerate is known as symplectic singularity, which admits symplectic resolution. So symplectic singularities are abundant. There are plenty of examples of symplectic singularity. But symplectic resolutions are extremely rare. So what happens here is that chi sigma G SL and C is always a symplectic singularity. Always is a symplectic singularity. Which admits symplectic resolution. It's symplectic resolution only, well, first of all, when G equals to 1 n arbitrary, that's a well-known case, or in one extra example, when the Gn equals to 2, 2. And this is this one. Now, there is kind of, if you have a symplectic resolution, then at least in the case when your variety is equipped with a C star action, this one is not. This is not. This resolution leads to the necessarily leads to the flat Poisson deformation of the coordinate ring. And this flat Poisson deformation will be precisely the spherical subalgebra of the genus 1 Daha. Now, here, we know that it admits symplectic resolution, but kind of this theorem doesn't really give you the presentation in terms of generators and relations of symplectic resolution. But our constructions at least gives you the presentation in terms of generators and relations of the flat Poisson deformation. So you see, if you start with the genus 1 case, you had Macdonald operator, you had the multiplication operator. You can solve for the monomial basis there, right? By introducing Q commutators. Turns out that you can do precisely that in our case. And the last A-U-T is a flat monomial basis. Basis, two parameter deformation. Of the coordinate ring of genus 2 character variety of coordinate ring of chi sigma 2 SL 2 C. And the way it is proved is that you construct a monomial basis on this algebra. You construct a monomial basis on this algebra, and this monomial basis resembles a lot in how you prove the basis on the universal enveloping algebra by the Poicare-Birkhoff Witt theorem. So essentially, you boil down the basis on the algebra of non-commutative operators to the basis on its commutative counterpart. So you find the number of normal ordering relations, right, which bring every polynomial to a combination of normally ordered monomials, and then you kind of you prove that what you had in the commutative case gives you precisely the basis in the non-commutative case. Okay, so but everything is more complicated because your commutative counterpart is no longer a polynomial algebra. This is a very kind of, in fact, the presentation of this algebra was not in the literature. So kind of a byproduct that we found a very nice presentation of this algebra. So let me see how much detail I really want to say about it. None. Sorry. So the idea is essentially to start with these generators, with these 6 generators, and those act like simple roots. Then you look at sufficiently many Q commutators constructed of these simple roots, and between the original generators and all the Q commutators will be the normal ordering relations. Simply, but in this case, those will be nonlinear. Those will be nonlinear, but in subleading degrees. And you can actually could use 15 generators, 15 generators. Now, 15 generators. And let's say that the classical counterpart has 18 relations. But there is an order 6 automorphism from the mapping class group, which cyclically permutes those generators. So there's only 3 types of generators, and there's only 19. And there's only 4 types of the relations. And that's it. So we found the binomial basis. We proved that it's a flat Poisson deformation. As a byproduct, we both found the presentation of the skein algebra in terms of generators and relation. We found the presentation of this ring, and we found a flat Poisson deformation of this coordinate ring, which is conjecturally the one dictated by the existence of the resolution. But that part is work in progress. So, okay. So thank you all very much for your attention. I'll be happy to answer the question.
Any torus section on the chracter variety?
What?
Any torus section on that?
No, excellent question. So now in the class of symplectic resolutions, the one equipped with a torus action plays special role. Those are conic symplectic resolutions. And in this philosophy, where you think about the symplectic resolutions as the Lie algebra, the ones with a C star action is a Lie algebra. This is Lie group, or that Lie algebra, because kind of even in the genus 1 case, you will have 4 singular points corresponding to the sign representation. If you look essentially at the vicinity of the trivial representation or any other singular point, you will get the variety which is equipped with a C star action, and this will be like a Lie algebra for this Lie group. In this case, it will be if you essentially look at the vicinity of the trivial representation of the pi1 of sigma 2. That will be related to the singularities considered by Len and Serger.
Yeah, but do you have any other kind of the flat deformation for this chracter variety?
Well, I mean, so flat deformations are controlled by Poisson cohomology.
Yeah.
So, and I didn't do that calculation on my own, but I know that this one is one-dimensional, so this should be the only one here. But that's actually a good that's a very good point.
Okay, let's see the speaker.